All right, so our next step is going to be to look at some graphs using technology and see if we can start to figure out what polynomials are going to look like. And we've already pointed out that we know the power functions, and I actually want to point out that we even can do a little bit better than that. We know how to apply transformations to the power functions, so we actually know how to graph something like that as well. And we're going to add to that being able to graph any factored polynomial. So we aren't trying to make a set of tools where we can graph every single polynomial by hand. We are trying to build up a set of tools where we can graph as many as possible, and we can get a good rough sketch. Okay, so what we want to focus on is things like this first example, where it's a combination of our basic function. So if it was just an x squared or just an x cubed or just an x, we already know how to graph that from our pre-calc 1. But as soon as we start to have more than one parent function or basic function, whatever you've heard them called, mixed together in one of these equations, we can't just apply transformations anymore. So I'm going to jump to Desmos for the rest of this, and I'm just going to walk through each of the 3 examples you see on this page. So take notes here, but I'm going to stick there instead of bouncing back and forth so that you can just follow along. Okay, so here's our first example. I've already typed the formula in. Remember that you can use this little keyboard down below to get some of the pre-built formatting, or to get exponents, you just do Shift and then the number 6 on your keyboard to get that little caret to give you an exponent. So let me know if you have any trouble typing those in. We are supposed to look at 4 different things, I guess, really. So the first one is the degree, and that actually comes from the equation, not necessarily the graph, although we do get good clues from the graph as well. The equation, we just want to look for the biggest power. So it doesn't matter what order I write these terms in, I can rearrange as needed. The biggest power I see is that x cubed. So this is degree 3, a third degree polynomial, otherwise known as a cubic. I'm just in the standard window that Desmos gives me, and it actually does a really nice job. I can see all of the local behavior. So local behavior is your x-intercepts, which we typically call zeros when we're working on polynomials, and your local maximums and minimums, which you can just call them that, or you'll see that I've typed up here and I called them extrema, which is just a more general term for local max and min all put together. It's local extrema, but I'm being a little lazy with my typing there. Okay, so this is just supposed to be a count for this second thing. I see 1, 2, 3 x-intercepts. I see a single local max and a single local min. So that's 3 zeros and 2 extrema for my third degree polynomial. Just as a reminder, local max min, I kind of glossed right over that. A good working definition of that is if you have something that you think is a local maximum or minimum, if you fix that point at the center of your window and zoom in, or if you imagine drawing a smaller circle around it, if you can find a window or a circle that's small enough that is the biggest y value you can see, that's a local maximum. If it's the smallest y value, it's a local minimum. Also note, so I'll give you an example. Let's see. There's a window. It's not quite centered, but you get the idea. You just don't want it right at the top or bottom so that you're not seeing other things. That is the, right there, that is the biggest y value that this function hits in this window. Okay. Also know that Desmos does a beautiful job of just telling you where those are. So you will have some questions that ask you to find a maximum or a minimum value, and you can just come in here and click, and it will automatically pick out a local max, a local min, or any intercept for you to just click on. So you can get any of those really easily from graphing in Desmos. Okay, so global behavior. The idea with global behavior is that you're zooming way out. So local behavior, you zoom in so you can see the zeros and the max mins. You can see it curving back and forth, doing this little up and down thing. Global behavior, we want to start zooming out. And you can just, if you're on a touch screen, you can just pinch. You can hit the plus or the minus to zoom in, zoom out. But we'll probably use a lot here is just going into the settings and playing with our y values. I don't really need to see more x values. I have this shooting right out the top and bottom of the graph pretty close to the middle. I need to see a lot more y's. And the goal here for global behavior is to zoom out so far that you can't see that x-intercepts exactly where they are and the maximums and minimums. It all just kind of mushes together, and all you're looking at is what's happening way out at the far ends of the graph. So let's go like -50 to 50. And this is just kind of a guessing game, a little trial and error, but it should be pretty quick and easy. I definitely still see the local maxes and mins and everything in there, so I'm going to go a little further. That's getting pretty close. They're starting to kind of mush into the x-axis. Let's just go really big. -5,000 to 5,000. And there's no like perfect window here. It's just kind of getting that local behavior to shrink down till it's not really distracting you from the overall shape anymore. And what I hope you notice here is this looks a lot like the plain old y equals x cubed, maybe not quite centered at the origin, but that general shape looks a lot like a y equals x cubed. So my global behavior is like a cubic. And since I typed it in the equals, you can even see that it gets pretty close to that y equals x cubed shape. Okay, so there's one graph to look at with some details summarized. I'm going to go ahead and turn that back off. Let's look at the second graph. The second graph is in a little bit different form. We have this y equals x times x minus 1 times x plus 2 times x plus 3 times x minus 4. It's in factored form, and factored form is going to be really helpful for a lot of the graphing of polynomials we do. So here's a graph that's catching some but not all of our local behavior. So you can definitely see some x-intercepts, some zeros. I almost see a maximum here, but it looks like there should be another maximum that I'm missing, and it looks like there's minimum here and a minimum here. Noticing that these are still quite a ways apart makes me think I'm going to have to make my y values quite a bit bigger. So again, I feel like I've got decent x values. I can see it going up and down. I can see all that behavior. And what polynomials will do is they'll go up and down a little bit, kind of like some sine and cosine behavior, although not nearly so perfectly symmetrical. And then they'll just shoot off to plus or minus infinity. So we're probably seeing all the up and down, but we're not quite capturing it with our y values. Let's try -20 to 20. Okay, that's pretty good. I catch both maximums. Again, assuming this is probably where it shoots off to negative infinity, and this is probably where it shoots up to positive infinity. You're going to have to kind of take my word for that until we get a couple of things established. I'm pretty much catching this minimum, but again, it looks like I'm a ways off from seeing the bottom of this little chunk right here. So I think I'm happy with the top of this graph. Let's go to -50 for the bottom. Still not seeing it. Okay. -100. Still not seeing it. See, I see it go down. I see it come back up, but I'm not quite seeing the bottom. 200. Okay, finally I catch it. I can see the bottom there. Sometimes what will happen is one of these will be so far down or so far up that you lose the other local behavior by the time you've zoomed out far enough to catch it. And that's kind of just the way it is sometimes. There's not really anything we can do about it. So we just have to understand as much as we can about these graphs so that we know that even though we've zoomed way out to catch that, there is still some other local behavior happening. Okay, I skipped one, degree, which is actually slightly tricky when you're in factored form, but I think you'll get used to it really quickly and have no problem. What we have to imagine here is what would happen if we multiplied this out. And you do not have to do it, but you can kind of imagine what you do. For example, I could pair those two together and I could FOIL it out and I'd get a quadratic. And I could pair these two together and I could FOIL them out and I'd get another quadratic. And I'd have to distribute an x into one of those two. So let's say we do the first one, we get a cubic out of this multiplied by a quadratic. So our highest power would be an x cubed and an x squared. And when we multiply those together, we get an x to the fifth. So this should be degree 5. Another way to do it, probably the simpler way, but still it's based on imagining multiplying it out, is just count how many x's would get multiplied together by the time you're all done. So 1x times a 1x times a 1x times a 1x times a 1x would give you 1x to the fifth. For degree, we only care about the power, but other times we might care about that coefficient. So that's why I'm saying the 1. Okay, zeros. I see 1, 2, 3, for 5 of those. So 5 zeros, degree 5 has 5 zeros. Local max and min, I see 2 maximums and 2 minimums. So 4 local extremes for this graph. And we're not trying to list where they are. Sometimes we will do that, but for now, we're just trying to count how many. Notice with those zeros, I wish I'd said it before I clicked out of them, you can hopefully see right where those came from. This is in factored form. So if we want to find zeros, we would set that equal to 0, and then you can take that apart. It doesn't matter how many factors there are. You can set each factor equal to 0. Setting x equal to 0 will give us the 0, 0. X minus 1 equal to 0 will give us the 1. X plus 2 will give us the negative 2, and so on. So we can actually see that just like with quadratics, a factored form will give us all those intercepts, which is a pretty good start for trying to graph these things. So that's why we'll focus on factored form, is because we get that to help us start the structure of our graph. Okay, global behavior. So we need to start zooming out. So I'm going to go in here and I'm going to say, I already went down quite a ways, but it's clearly not far enough. Let's go negative 2000 to 2000. Notice that whenever I have one side going down and one side going up, that's when I make both ends. I go up and down as I zoom out. Whereas if your graph goes down on both ends or up on both ends, you can only focus on one of those endpoints to zoom out. Okay, I still get a pretty good hump right here from that maximum, or that minimum, I'm sorry. So let's go a little bit further, maybe 5,000, 5,000. It's still showing quite well. 10,000. 10,000. Okay, if you get tired of it, you can always just go really big. I'm just going to stick an extra 0 in. And there we go. And honestly, it looks quite a bit like the last shape I saw. It has that x cubed shape. But I'm going to give you a little nudge and say that this is kind of linked to degree. So what I think we're actually seeing is an x to the 5th shape. And again, it doesn't have to match perfectly, but since I'm in Desmos, I'm typing those in. You can see that they are actually pretty close. So this is shaped a lot like an x to the 5th, which granted is similar to the x cubed shape, but that's going to be our tell, is what is the degree and how does that help us? Okay, so we have one more to look at, but before we do that, I want to summarize some things that I'm hoping you've spotted. I know it's only 2 examples, so it's kind of hard to think you have a pattern. But what I'd like us to see is that when we had degree 3, there was 3 zeros, 2 extrema, and the global behavior was an x cubed. When we had a 5th degree, we had 5 zeros, 4 extrema, and the global behavior was an x to the 5th. So what I'd like to propose as an idea here of what might be going on is that if it's an nth degree, it will have n zeros and n minus 1 extrema. And the global behavior will be an x to the n. Okay, so this is what I'm hoping you've kind of spotted happening and are maybe guessing right now. Okay, so now that we have that, let's look at this last one. So I've got that one typed in for us. Just looking at the formula, I can see that it's degree 4. Again, it doesn't matter what order those terms are in. It's that biggest power. So 4th degree polynomial, a quartic is what that's called. I can see 2 zeros, but I'm missing a little bit of that top piece. In fact, here, I'm just going to zoom out a little because we were kind of proposing that we should get 4 zeros, but notice I don't see, no matter how far out I go, I don't see it turning back around and coming up to get me 2 more zeros. So I'm going to look at that and say, well, it seems like that's actually all of our local behavior. And all I got was 2 zeros, and it's really just the one extreme. Let's see, my mouse isn't going. There we go. This point over here, that one can confuse people. We get the little flat spot. You'll see that in polynomials. And that's not a maximum or a minimum. What's basically happening there is it's like a minimum and a maximum kind of got mushed together, and it just made this flat spot. It is an inflection point. I see that upward bend and then that downward bend. So the bend definitely changed there, but it's not an extreme. It's not a maximum or a minimum. Okay, so our end behavior, we already got the top of this graph, so we're just going to try and look for way further down the bottom. I'm going to guess negative 500, negative 5,000. Well, that's not too bad. Let's see if I can shrink it down just a little. I mean, that's probably good enough. You can kind of see one little hump there. So if you don't like it, you can always go negative 10,000. Keep playing around, but I think I've got a pretty good idea of shape there. I am seeing that kind of parabola or x to the fourth shape that I've been predicting, but I also noticed that it's upside down. I would expect x squared or an x to the fourth to open up, and this one does not. So it looks to me like it's a y equals negative x to the fourth instead of y equals x to the fourth. And give or take a little bit here, it's fine that it's a little narrow, or you're just trying to get that general shape. So what turns out to be true is not that degree 4 means exactly 4 zeros, it's that it means at most 4 zeros. And that's the best we can do. It gives us a maximum number of zeros, and we can say there are at most 3 extrema. So it's an at most rule, not an exactly rule, which is not my favorite, but it does help a little bit with when I was telling you, can we get zoomed back in here? Let's see. Negative 20 to 20? Yeah, okay. That I thought I was probably seeing all of the local behavior. I was assuming that this doesn't turn around and come back down. It's because it's a cubic and I already see 3 zeros and 2 turning points, so I can make the assumption that I have caught all of my local behavior. Okay, one last thing I want to sneak in here is a little bit of important notation. So I am going to actually go back to our worksheet. Okay, so with the global behavior, what we're getting, sorry, I went a little too far there. We said that this first one had global behavior like y equals x cubed. What's important about that is just what's happening as x gets really, really big or really, really small. And this notation that I'm doing here is like the beginning of the limit notation you'll use in calculus. So we read that as x approaches infinity or as x approaches negative infinity. And what we're summarizing here is what happens to y. So if you're shaped like an x cubed, as x gets really big, so does y. And as x gets really small, so does y. So looking back in Desmos, if we go back to our zoomed way out, what we're imagining here is motion. We're saying, okay, x is getting bigger and bigger and bigger. What happens to y? It also gets bigger and bigger. So that arrow really does mean move towards whatever's on the other side. So move towards negative infinity. What happens to your y? So we're going to start using that notation just to get used to it. It's nothing too tricky, but I think it's helpful to start to get that in your head. And notice that with this one, our behavior is like a negative x to the fourth. There we go. So we would say as x goes to infinity, y goes to negative infinity, and as x goes to negative infinity, y also goes to negative infinity. So they don't always match up. Sometimes they go opposite directions, sometimes they don't. But please start thinking about that notation a little bit. Okay, last thing in this already quite long video, I just want to look at the properties. We basically have seen all of this now. So smooth and continuous, these are actually fairly formal terms, but we're using them a little informally. Smooth means you don't have any sharp corners. So when we were looking at the bend in those polynomials, there was never like this, never a sharp corner. They always curve nicely. They're smooth. There's no sharp angles in them. And continuous A nice working definition for that is you can draw it without picking up your pencil. So if you have to stop and draw a hole in a graph, it's not continuous. If you have to stop and draw an asymptote, it's not continuous. Sine is continuous, so is cosine. You can draw that whole way without picking up your pencil. Polynomials are always continuous. There's no breaks, no jumps, no asymptotes. There's no discontinuities at all. You also hopefully spotted that the domain is always all real numbers. We're taking numbers and raising them to positive integer powers, multiplying by constants, adding and subtracting. None of those operations allow for a domain problem. Domain problems happen when you divide by 0, take square roots of negatives, take logs of negatives, things like that. None of that's happening. Here's our at most rule. So we went over that. An nth degree polynomial has at most n zeros and n minus 1 turning point. This is written formally, but we talked a bit about the factors. If your polynomial is in factored form, that should automatically tell you an x-intercept or a 0. And then this last one I didn't quite fully spell out, I don't think. The global behavior is determined by the leading term. So we got that the power comes from the degree, that highest power, and that's the leading term has the highest power. But the coefficient does matter as well. So this example that we had up is a good one. We had a negative 1/4 x to the 4th. I don't really care whether or not you include the 1/4. It doesn't greatly change how I'm visualizing this, especially when I'm not even usually showing a vertical scale on the graph that I'll draw down on my paper. But you could put it in and notice it does match a little bit more. So what I care about is just that the far left and right sides are going the right direction. So the minus is very important. You can choose whether or not to include that 1/4. There is one last thing on our list. It's this multiplicity, so we'll get into that shortly. I will just say that it ties back into these basic shapes. So if you're in a factored form, we know that each factor tells us an x-intercept, and if any of your factors have a power, it actually affects the shape at that x-intercept. So second and fourth powers will give us this kind of bounce off the axis shape, and third and fifth powers, or any odd powers, will give us this funny flat spot and then just continue going in the same direction. So that's still coming. Otherwise, that's a pretty good list of the tools that we use to help us sketch polynomials. All right, thanks for watching this long one.